Watch Mr. Wizard. That's what all the kids in the neighborhood call him, because he shows them the magic and mystery of science in everyday living.
Mr. Wizard?
Oh, hi, Phil. Come on in.
Oh, hi, Mr. Wizard.
Hi.
What's going on?
Well, look. Come on, stay out there. You'll see. Now, watch. See that pencil? See my eyes?
You crossed your eyes.
Yeah. You can laugh, but and it may look funny, but actually that's a very complicated business with your eyes there. In fact, there's a computer built into my head that's automatically computing all kinds of angles. And there is in yours, too. In fact, you'll try it later, and you'll see how funny you look, too. You'll see later. Because today we're going to investigate how far away is it? When something is at a certain distance, how do you know how far away it is? And is it? And when something is at a real far distance, what are ways that you can devise, or that man has devised for figuring out how far away things are?
Look at it.
Okay, what is this?
It's a ruler.
How big is it?
12 inches.
How far away is it?
It's close. I don't know.
Real close, okay.
4 inches.
Now, if that's the case, tell me now, what is this?
A ruler.
How big is it?
12 inches.
How far away is it?
A couple of feet.
How do you know?
Well, oh, the ruler looks smaller
I
to
thought
me.
you said it was 12 inches.
It is.
Well, if it's 12 inches, how come it looks smaller?
Because you're further away.
Well, you see the problem?
Yeah, I see the problem.
That you think of a ruler as being 12 inches because you have it close by, and it's part of the fact that it's way across the room and looks smaller. You still say it's 12 inches. But you know
I
also...
know it's 12 inches.
Well, it's not 12 inches when it's across the room. It's obviously something smaller. But you assume that it still is 12 inches.
12 inches here, it must be 12 inches back there.
And that the reason it looks smaller is because it's so far away.
Yeah.
Now, artists use this all the time. This is part of your whole way of looking at things. In fact, over here on the wall is a picture by an artist, and he has used this to help create things at a distance because of their relative size. Now, see, this is a picture by Utrillo.
I can see the difference.
Right.
This house, he drew this big,
Mm-hmm.
higher, and the ones down here are shorter. It's
They're supposed to be roughly the same height, too, aren't they?
yeah, but it's perspective.
Yeah,
I
that's
think
right,
He
that's
wanted to give the idea of a street going down this way.
Look at the size of the people.
Yeah.
Is this lady a midget and this lady a giant?
No, it's just that. Well, it's like when you look at something. If I looked at you and someone in back of you,
Mhm.
he'd look smaller.
Right.
Even if he might even be bigger than you.
So that's one way that you can tell how far away something is because it looks smaller, and you know what size it is when it's up close, so if it's small, it must be far away.
Yeah.
Now, I can sort of, well, let's do it this way. When you're in the Air Force and you're a pilot, you have to take a test called depth perception, in which you line up two sticks, and you're supposed to get them so that they're exactly parallel, right opposite each other, but you're looking at them from this distance. So we're going to do that.
Okay.
And the sticks I have are over here. They're pencils. So you come over here and you stand about over here, and you look down over here, and here you will see two pencils in cork. See them?
Yeah, I see him.
Okay, now, we'll keep one movable and we'll leave the other one stationary, and I'll move this one back and forth, and you tell me where to put them so that they're exactly parallel now. What should I do? Move it forward, back, or what?
Forward, I would think.
Forward?
Keep on
Tell me
coming.
when to stop.
Keep on coming. Oh, maybe you better go back a little bit.
About
I
like
want to
that?
try and get them level, then I should know they're...
Like that?
Yeah, that's good.
Okay, now you think they're parallel now. See, this
Yeah,
is...
they look parallel.
Okay, if you think so, you come over here once.
You can see they're right next to
Come on.
What'd I do?
I thought you said they were opposite each other. Look how far apart they are.
They look like they were right next
Okay,
to
now,
each other.
yeah, go ahead, put them together. You had the right idea there. You see why you thought they were the same?
Yeah, they are the same size.
That's right.
That's a dirty trick.
Yeah, it was a dirty trick, wasn't it?
Yeah.
But there you see how you made the assumption that they were both the same size, and therefore, to make them parallel, you had to get the short one closer to you,
Closer to
and
that
the long one
back.
further away, and you were about a foot off.
But they sure, yeah, they sure looked like
They
they
sure
were.
look like it. So you see, you can play tricks on people and some of the funhouse games and things like that are done based on the idea that you judge how far away something is by its size. Now, you also judge how far away something is because you have two eyes.
I think so.
Yeah, let me move this out of the way and show you what I mean. Let's prove, first of all, that you have two eyes. And that's not as facetious as it sounds. The fact that you see two different images, everybody knows you have two eyes, but they don't often think that you really see two different things with your two eyes. Here, let's take these two pencils. And, well, first of all, put your hands down at your side, then bring your two fingers up like this and look way across the room. In other words, get your eyes parallel so that you look right straight across the room. Now, bring your two fingers up like that and gradually bring them together until someplace right there in the middle, you'll see them overlap, and you'll see a little sausage.
Hey, something's floating around in the middle.
Yeah. Now, keep your eyes focused on the other side of the room.
I am.
Yeah.
It's like the two ends of my fingers are, you know, they're meeting and forming a little thing in the middle.
Now,
but
why is that, you suppose?
Well, I guess it's that I'm saying this finger with this eye,
yes,
and this finger with this eye, and then they're kind of meeting.
And you're blending
it's
the
like
two together. And notice that makes a difference. You have to keep looking across the room. If you look right at the fingers, the thing goes away, doesn't it? Yeah. Now, the fact that you have two eyes is very helpful in another way. Here, you take this pencil and hold this pencil like that with the eraser sticking out here, and hold this pencil with the point sticking out here. And what I want you to do is to bring them together and touch them. But hold your hands down to your sides, and now close one eye and bring them up and try to move them together and touch. Now try the other eye this time. You missed.
Yeah, it was a little bit better.
Now try it with two eyes. Leave them both open. Oh, you went a little slower, too.
Yeah, well, but this at least I can see what I'm doing.
Yeah. Why is it easier?
Oh, because I'm getting, with just one eye, I can only really see one pencil, and this one is just kind of out of the edge.
Also the difference is here with one eye, you were doing this business of the two
trying
pencils.
To get them parallel
and with two eyes, you begin to see some depth. In fact, let's investigate that a little further, the fact that you have two eyes and the fact that you see two images and how that's important. Now, let's do that by, come over here. See this, this stand here? I'll put it about up here like this. And you go on over there, over on the other side of the room, and you line yourself up so that when you look at this rod, you line it up with what it looks like in the back of the room over there, and then close one eye and look now. Now, what do you see? The rod. See, now notice where the rod is. Where is the rod?
It's kind of right in the middle.
Okay. Now close that eye and open the other one. Where is it? There.
Go on.
Right here?
It's way.
There it is there, right?
Yeah.
Okay, now close that eye and open the other one again. Close that eye and open the other one.
Okay.
It jumped how far?
And now it's over on the other side of the window.
In other words, when you look from one eye to the other here, it jumps a considerable distance, right? Mm-hmm. Now I'll move this a little closer to the wall. Okay, now try the other eye and see how far does it jump this time.
Not as far. The other time it was off the window.
Try first one eye and then the other, back and forth, back and forth. One eye and then the other, huh? See?
Gee, there's a big difference.
Okay, now look at it with one eye again, and I'm going to take the stand and bring it right up practically next to the wall. And
okay, I see where it is.
Okay, now look at the other eye.
Hey.
Hardly jump?
Yeah, it's a very little jump.
Try looking with one eye and then the other there. Hardly moved at all?
It's a very little jump. Before, I was jumping right off the window, but now it's very little.
Okay, well now, come on over here and let me show you what we have really been looking at here. Here, you want to hold that side of this little drawing pad? What we really were doing was, I had you out here like this, and you have two eyes. And now I took that little stand and I put it here like this. And I said, if you look with one eye, you lined it up with the window back here, didn't you? Mm-hmm. And if you look with the other eye, you lined it up with this side of the window over here.
Oh, no wonder
and it jumped
so
from there to
far
there,
apart.
didn't it?
Yeah.
Now, when I moved this over here like this, you now looked at it, you now lined it up there, and then you lined it up here, so it didn't jump nearly as far.
Oh.
And then if I move, finally I put the light stand here, and it hardly moved at all, did it?
Oh, I see. That's what you were talking about with that, like the little computer built in.
So what you were doing with your eyes when you look with both eyes at this thing, your eye, because it computes the angle here inside this brain, I should really make a smaller brain for you, because that's my brain, they're a big one. Your brain automatically computes this distance and says, well, if I get this image with that eye and this image with that eye, the object ought to be out about there someplace. And if I get this kind of an angle, the object should be out there. In fact, that's what you do without thinking. Here, remember when you came in, I was experimenting with the cross-eye business? Your eyes automatically move back and forth following that distance, and when you get to a certain distance, then you begin to look cross-eyed. In fact, you can feel the muscles tugging in your eyes, can't you? So that's where you have built-in rangefinder and computer right inside of your head. And there's a certain distance in which your eyes will no longer go in, and that's up to about, 10, 11 inches, 8, depends on various people can move their eyes a certain distance. Now, let us see if we can use that principle to actually compute how far away something is, but what would have happened if your eyes were this far apart?
I guess I would have been able to...
Would be easier to figure, wouldn't it? Because the angles, the further apart it is, the more angle they're going to be. If your eyes are real close together, there would be hardly any difference between them. Mm-hmm. Okay, that's the principle on which rangefinders are based, and I have one all set up. Come on over here, I'll show you how we can use it. Remember that piece of wood that we had
It's the same thing.
Same thing, but this time we're going to use it as a rangefinder. Now, here, this piece of wood is at a right angle here, and here is a yardstick with a mirror pasted on one end and a little pivot here. See that? Mm-hmm. That pivot can go right here in this hole. Now the mirror is, out in this direction. Now, when you adjust that yardstick, what happens to that mirror?
Oh, it's turning.
See how it turns back and forth?
Yeah.
Okay. Now, notice there's another mirror right here at the bottom of this line.
Oh, it's right in the center of that line.
Yes, in fact, I'll put my finger out here. You see it? See the finger there?
Yeah,
in the mirror?
I see it moving.
Okay. Now, what I'd like you to...
it's hitting at a 45-degree angle and then bouncing off.
Okay, kind of like a periscope.
Yeah.
Now, you look right down this line and line this line up with the piece of white tape I pasted there on the edge of the window. You see it? Line it right straight up, right straight down here with the piece of tape on the edge of it.
That black line, though.
About like that?
Yeah,
with that black line. Now you move the yardstick until you see that white line in the reflection in the mirror. Oh, I think it went too far now.
What am I passing? Oh, there it is.
Okay, now you line that up exactly. Okay, now what you have done is you've computed these two angles and you've converged both the images of that line on that line down there. Now, I have a yardstick down, or a tape measure down over here. You go around to the other side of this, and I'll bring the tape measure over, and we'll see how close you are. See, I have it tacked up over there.
You have it marked over here.
I have it marked on that side over there. So you read, what does it say right there?
It says 18 feet.
18 feet. Here's the tape measure.
18 feet?
Right to the center of that mirror.
This is exact.
Yes, it's quite exact. In fact, if you make sure that the bearings here aren't loose or anything, you can get quite accurate results with it.
Well, if you really made it very accurate, I guess you'd tell it to the
Well,
inch.
this is exactly the way a camera rangefinder works. In some cameras you can move two images together.
You have to line it up.
And they also use this kind of a rangefinder in naval. When they want to figure out how far away a ship is to fire at it, they can use a system like this. Well,
I guess I could use on almost anything.
Okay, now the reason why this was more accurate than your eye would possibly be is because we had this distance between the two images, didn't we?
Oh, and if the base is bigger, you get more of an angle.
You get more of an angle. Now let's make the base even bigger yet. And they use that, for instance, let's say that you are a satellite spotter, and it's your responsibility to send to central headquarters the information about how high the satellite is when it goes over your position. And here's how you might do that. Here you are with your computers, and you know that the satellite is going to go someplace over in this area. You establish two sighting stations, let's say 10 miles apart.
Here's the base.
That's the base, just like the two mirrors before. Now, when the satellite comes over, at exact instant, you could line it up as it went over here, couldn't you? Let's say that when you line it up, it says 50 degrees. So now you know that the satellite lies someplace along this line, don't you? Mm-hmm. But you have no idea where.
Oh, and that's where this other one comes in.
Okay, now, at the same time, at the exact same instant, the other one says 45 degrees. So you could set the computer down here at 45. Okay, what's the height of the satellite?
430, I guess.
30 or 40, there's 450, right? 450 miles.
About 35, I guess.
435 miles. And that's actually the systems that they use. They use, of course, much more complicated.
But it has to be at the same exact second, doesn't it? Yeah. Or else this one would be over here and this one would be
And you can
down
see now
here.
why it's extremely important that scientists have precise timing mechanisms so that they know exactly, they're both doing this at exactly the same instant. Otherwise, if they time at two different instances. This is also used in reverse by a navigator. Let's say you're in an airplane and you don't know where you are. You could have a sighting device or a radio range finding device that would figure out this angle to this radio station. And you'd know that you were someplace along here. Now you swing the antenna around and get a fix on the other radio station over here, and you could draw this line and you'd say, that's where I am.
Oh.
See, just the reverse.
You can work it reverse.
Just the reverse.
But this is the way they do it.
The important point is that you figure out two angles from some kind of a baseline, and that's how you know where you are. Now, what would happen if we got the baseline even further yet? This was 10, 15 miles.
I guess it would be even more accurate.
What is the biggest baseline that you could think of?
I guess the Earth.
In other words, from one side of the Earth to the other.
Yeah.
Okay, but if you're going to measure the distance to a star, that's not nearly far enough.
Oh, I think I know what it is.
What?
Well, I know scientists, they take a reading on a star, one in the spring and one in the fall.
Why should they do that?
Well, because then
Seems
they're
like
using
a
the
long-
whole orbit and the whole length.
Here, you show me what you mean.
Well,
What do you mean, the whole orbit?
okay, here's the sun,
Yeah.
and
Okay.
the Earth goes around the sun,
Yeah.
and here's the Earth in spring, and
Yeah.
then here's the Earth in fall.
Okay, now what do you do?
So if the star is up here,
Yeah.
they could take a reading here,
Mhm.
and then a reading here,
Okay.
and then they have a baseline.
Okay, what's that? How long is that baseline?
What's
the distance to the sun?
93 million miles to the
From
sun.
the Earth to the Sun is 93 million miles, so that's only the radius here.
Oh,
So what's the diameter?
186.
186
186
million
million
miles.
miles. That's quite a baseline.
Yeah, it's quite a baseline, and that's how they can figure the distance to various stars quite accurately, getting that baseline of
This is the longest one, I guess.
the diameter of the Earth orbit. Now, there's another method that you can tell how far away something is. Notice all of these we're figuring out some kind of an angle. There's another method that you can use to judge how far away something is. Maybe I can explain it best by using this spring down here. See it?
Oh.
You stay there, hang on to that end, and I'm going to pull this end across the floor. Okay, now you just tap the spring like that and watch what happens. What do you notice?
What? It hits your side and bounces back.
Yes, there's an echo there, isn't there?
Yeah. Echo!
The energy goes up here and is bounced back over here. Okay, now, why don't you hit it and time roughly by counting, like 1, 2, 1, 2, how long it takes to go up and back.
1, 2. 1, 2. 1, 2.
You should do 1 at the time when you hit, though. 1, 2, 3. 1, 2, 3. That's it.
1, 2, 3. 1.
Okay, remember that, because now I'm going to move this in a little bit. Say it here. Now try.
1, 2, 1, 2, 3. 1, 2, 3.
Let me tighten this up so that we get the same tension as you had before. Now try.
1, 2, 3. 1, 2, 3. 1, 2, 3.
How can you tell now how far away this is as compared to the first position?
Well, it sure to be a lot closer.
Why?
Because it's coming back a lot faster.
Yes, it's coming back a lot faster. Therefore, this is the system now. What was I illustrating with this?
Well, it's like an echo, really.
Yes, all right. You pretend that you're standing at the end of a canyon, and you say hello, and I'll be the echo, and you tell me how far the canyon is first.
Hello!
Hello!
You're pretty close.
Pretty close. Short canyon. Okay,
Yeah.
try it again.
Hello!
Hello! What you got? Try it again.
Hello!
Hello!
You're over the next
Yes,
state.
a long way.
Yeah.
Now, how do you know?
Well, because it took a long time to get back.
You know that sound travels 1,100 feet per second, so therefore, if it
Second.
took 4 seconds, it must be 4,400 feet away, on one way.
All I know is that
It's a long distance
it's
away.
a
It
long
takes
distance away.
Now, isn't that how? Can't you see how? Would you know of anybody that really uses that system?
The bat.
Oh,
Well, he sends out a wave, and he can tell at night how how close something is by how soon it bounces back.
Yeah, and he sends a very high frequency sound that we can't hear. And scientists discovered this only when they began to record sounds way above the audible range, and that's how he uses. Porpoises also do this.
Porpoises?
You know, the little animals that they're
water?
testing now. Yes, and they've discovered they send out sounds and use somewhat that same system. Something else in the water uses that. It's called sonar.
Oh, and the submarines.
Yeah, what do they do?
Well, they send out the wave and bounces off another. Radar, too.
Yes, radar, but radar doesn't use sound. What is
Radio.
it? Radio wave. In fact, let me see if I can show you how radar would work on a satellite, and see if I can illustrate it here with an oscilloscope. Let's assume that there's a satellite up here, and let's assume that you want to figure out how far away it is, and you send a radio wave up here, and it bounces back, and it takes 2 seconds from the time it left here until it gets back. Okay, how long does it take to go one direction?
Well, in 1 second.
1 second. Okay, how far away is the satellite?
Well, first you have to know how long it takes for radio waves to travel.
Radio waves travel 186,000 miles per second.
Oh, well, that's 186,000 miles.
186,000 miles away.
Is it that simple?
Well, it seems like it's that simple in theory. The problem is, what happens if it's closer than 1 second? Then you start having to getting half second.
Dividing.
Divide. In fact, what if it's only a couple of miles away? Then you're down to 1,000th of a second. Well, that's not so difficult with an oscilloscope. In fact, I have one over here, and let me see if I can show you how we can make that work. Here is an oscilloscope. Looks something like a radar screen, doesn't it?
Mm-hmm.
And in order to get to use it, we have to make a trace go across here. Down here is a little electronic metronome, and back here is a microphone. Now, when this begins to tick, the sound from this microphone, we can send it up here and make it go across on this scope. Now, in order to see this better, you want to go turn off the light over there by the switch in the wall?
Okay.
Now, this line is sweeping across here. It's started by the sound of that ticking. In fact, there's a control on the metronome there, or they turn it down. You'll see that. See, the slower you go, the slower the line goes, and the faster you go, the faster the line appears. Now, I've got this set by a control here, so this line moves across the face of the scope. See those little squares in there?
Yeah.
Those are a centimeter. It goes from one side of the line to the other, in other words, in 1 centimeter, in 1,000th of a second.
1,000th of a second?
Yes, 1,000th of a second it
You mean
takes.
it's sweeping across so fast?
Yes, and you can change the speed with which it sweeps over here, and I've got it set so that it goes in one of those little lines in 1,000th of a second. All right? How fast does sound travel?
1,100.
1,100 feet per second. Let's assume, just for our purpose, that it travels at 1,000 feet per second.
Mm-hmm.
We now know that if we can get some kind of a echo or something along here, we'll be able to measure the distance right over here.
1 foot
Well,
per
here's
square.
how we'll do that. This microphone is starting the sweep across here. But I have another microphone here. And right here is the volume control for it. I'll turn it on. Now
Look at the way it... Whoop.
Yeah, the sound from this microphone now is distorting that line, isn't it?
It's jumping
See
up,
how it makes
yeah.
it jump? And when we talk, you can see the jump. Now, you hold it about this distance away over here, and I'll turn the gain right here, this volume on this amplifier here. Notice that there's a little space in there.
It's pretty straight whenever I talk, isn't it?
Well, don't talk for a minute, and notice that line right there.
It's about 1 foot.
Yeah, all right. Now
One square, 1
square,
foot.
1 foot. Now, here, I'll come around over here, and I'll hold the microphone, and you adjust the volume so that the height is right here. I'll hold it here right next to it. Now it's practically right there. That there's at no distance. Now I'll go out here about this far. How far away am I?
1.5 feet, maybe?
Well, look at the distance.
1.5 feet. That's
About a
pretty
foot and a
close.
half, right? Now, you just watch the scope here. And I'm going to move, and you tell me where I am by just looking at it.
2 feet, 3 feet, 4. Must be about 5 now. 7? You're getting off the range. 5, 4, 3, 2, 1. Blast off!
See how you could tell how far away I was now? Now, we're not doing, this is not radar, remember, where this is by sound. So what is the difference between what we're doing and what radar does?
Radar bounces it like into this microphone and then bounces it back.
In other words,
this only goes one way.
That's right. I was just telling the distance one way. If we were really using radar, we'd have this sensitive microphone here. We'd have the first microphone giving us our pulse, and then we'd have a sensitive microphone that would detect the echo coming off of the object and timing that difference.
Well, it has to be something that'll echo back.
Right, and it has to be, and the computers then divide the time in half automatically.
Yeah.
And they can do that by setting the proper sweep. Well, let me turn this thing down before it drives us absolutely crazy. You can now see the system whereby you find where you are is based on all kinds of things. First of all, probably the most important one, the one that you use in your everyday life. How do you tell where something is in your everyday life?
Well, you can usually tell because you know the original size and then by how small it is, how far
tell
away
the difference.
it is.
You can tell the difference, well, for instance, between two people when one is close and the other is further away by just their size.
Yeah.
And I can fool you, can't I? How?
Yeah, like with, you took pencils of different sizes.
In fun houses, they do that. In fact, stage designers use that all the time, and painters. They make a small person, and you assume that it's further away.
Yeah.
So that's one way of doing it. Then, how about the next system, whereby you find out how far something...
Well, you have to compensate for parallax.
Parallax, the fact that you
Parallax.
have two eyes. And how's the easiest way to prove that?
With
little
your fingers,
sausage.
find a little sausage.
The little sausage. You have two images, and how then, why do you, how can you use the fact that you see two images?
Well, you can use it on, like, your rangefinder.
Well, you have the computer inside your head that tells you about these
then
angles.
it compensates for it, and you, the cross-eyed.
Then what happens when you have two eyes but make them further apart?
Well, you get more accuracy, because a bigger base, more accuracy.
More accuracy. And what was that? The rangefinder.
That was in the rangefinder, and in the tracking station.
And the tracking
too,
stations
yeah.
for the satellites, fine. And now, what is the biggest base that you can think of? Remember?
The diameter of the Earth's orbit.
Right, 186
6
million
million miles.
base. And finally, then, we found that the other system was a system of what?
Of echo.
Echoes, in sound or in radar, radio waves. And we illustrated it here using sound, although in actual radar they use radio waves, and we didn't bounce it, we measured it directly. But if, let's pretend we are, and you watch this line, how it moves back and forth, and now you're using the very latest scientific method of finding out how far away it is.